In our last PowerPoint, we talked about the basic electrical concepts, that of the voltage, amperage, current, watts. We also talked about series and parallel circuits. And I basically told you that electricity and electrical concepts are the core of the HVAC trade. So now we have to talk about meters because your meter is going to be your primary troubleshooting tool to find out problems having to do with a circuit. Okay, it's your most often tool used as an HVAC technician, should probably be the first tool out of your bag, not only for safety purposes, but also for troubleshooting, and it should be the last tool you put away. Okay, I do recommend that if you have a meter, you read the manual that came with the meter and try to understand all the functions. There are two types of meters on the market. You have your analog meters. These are very infrequent now, but they've been the workforce for years. We're the first meters on the market, and they're extremely sensitive and don't stand up very well to being tossed around trucks. Okay, they're still used today when technicians are looking for extremely accurate measurements. They are much more accurate than the digital meters. An example of an analog meter is this. Basically, analog meter has a scale or a number of scales and a needle, and then you'll have different inputs or an adjustment knob to select the scale. Digital meters have almost completely replaced the analog ones. Okay, as with everything else, we've gone to digital because they're easy, they don't need adjustment, they don't need a lot of calibration, and they can stand up better to being dropped, tossed around, and they can stand up to a wide range of temperatures. Digital meters are relatively accurate and usually auto range. In other words, you don't have to select a range on them anymore. One thing to add to this, digital meters do depend on their battery strength. So if you have a meter that's running low on battery, you probably need to replace the batteries and just watch that occasionally. Example of a digital meter is this. This is an older one, but the newer ones, they'll actually interface also to your smartphones, your iPads, iPods. They're more and more interfacing with computers. Okay, there are several basic rules of electricity we have to understand prior to understanding what a meter is telling you. A meter is not going to tell you what the problem is. All it's going to have to do is tell you, it's going to help you find where the problem is. Okay, these rules that we're going to talk about are based on voltage and resistance. Okay, first of all, series. You're going to hear us talk about that things are in series with something else. Series just means in the same line as. Okay, we're going to talk about series circuit in the next section, but for example, for now, the red ball is in series with the yellow ball and the green ball. Oops, this ball here was supposed to be yellow and it just didn't end up with that. Okay, so these three are in series with each other. You see that there's a single path. And if this was a circuit, there would be no way for electricity to get directly from this orange to this light blue and back to the dark blue. For electricity to flow, we have to go through the orange, the dark blue, and the light blue. Parallel means, again, next to. We talk about things being in parallel with each other. All it means is next to. Again, we're going to talk more about parallel circuits, but for now, the orange ball, the dark blue, and the light blue are all in parallel with each other. If this was a circuit, okay, and if we drew a line down here to connect them all and connect that, okay, every item in here would be able to get voltage. Okay, because they're all next to. You don't have to flow through one to the other. Okay, we talk about open circuits. Open circuits that are circuits that do not have a complete path for electricity to flow. Okay, circuits require a source, switch, path, and a load. If any of these components has a break or open in it, the current will not complete the circuit. Okay, this is an example of a basic open circuit. We come from line, we come to switch 1, SW1, but it's open, so current can't flow from this point to this point because there's a break in the circuit. Therefore, light bulb B1 will not be energized. Again, there's a break in the circuit. Now if I close the switch, then we would have a complete path for electricity to flow. When you measure voltage across an open circuit, you'll always get a reading of source voltage. When you measure resistance across an open circuit, you'll always get a reading at infinite or OL on a lot of the digital meters for open line. So again, source is whatever voltage is connected to. So if I go back to this circuit here, and if I took a voltage reading from there to there, I would get 120 volts because there's no complete path for electricity to flow. A closed or complete circuit is one that has a complete path, source, switch, and load. The load is operational in a complete circuit, and the switch is closed in a complete circuit. This is an example of a complete circuit. Same circuit we talked about with the open circuit, but now it's complete. So we go from line to switch 1, out of switch 1 to B1, back to neutral. So I now have a complete path for electricity to flow, and light bulb B1 would be energized. When measuring voltage across a switch in a complete circuit, you'll get 0 volts. When measuring voltage across a complete circuit, you'll get source. So in other words, if I go from L to N here, I'm going to get source. 120 volts if this was a 120 volt source. If I measure from, let's get a pen. If I measure from that point to that point in this circuit, I'm going to get 0 volts because there's no difference in potential, and we'll talk more about that in a minute. Okay. A short circuit is a circuit we absolutely want to avoid. Okay, if you look at this circuit, we see we're missing a load. So I have a complete wire from all the way from line back to neutral. Okay, this is a dangerous situation. A short circuit does not have a load or enough resistance to control the flow of current. A short circuit should immediately trip the circuit breaker if it's on line voltage. A short circuit on a transformer can either blow the fuse or cause the transformer to be permanently damaged. A lot of times it will actually melt down and you'll have a lot of smoke coming out of the transformer. Short circuits are dangerous and they need to be avoided. So again, make sure every circuit you work with has a load that's wired in it. You should never have something bypassing a load. The voltage across loads is a meter reading you can take. You put the meter lead on each side of the load. Voltage across a load is identical if the load is working or if the load is bad. Okay, if you have all the switches closed and measure voltage across a load, the circuit is good. If the load is not working, then you have a bad load. If the load is working, then the voltage you read is the voltage that the load is using. And I'll show you an example of that in a minute. Current, or the amperage you measure, will be 0 in an open circuit because there's no voltage being used. If the switch is open, the circuit is not using anything. In a closed circuit, the amperage you measure may change based on where you take your readings. Meters are going to measure voltage, current, resistance, capacitance, frequency, and temperature. Voltage is one of the most frequent measurements you make. To measure voltage, turn your meter on, set it to volts or V depending on your meter shows. Make sure your leads are plugged in to the correct place on the meter. Put the leads in parallel, that's next to the point of the circuit you're trying to measure. Hold the lead steady. Don't touch any of the metal to your fingers or to each other. Watch the display until the meter stabilizes on a number that is your reading. So again, we go voltage across an open switch. We put our meters here. Okay, I have one lead there, one lead there. It's 120 volts. Basic rule you have to learn. Voltage across an open switch is always source. Now I close the switch. Okay, voltage across a closed switch changes to 0. Open switch is source, closed switch is 0. Now, we change up to the load. Again, we have a meter lead here and a meter lead there. Voltage across a non-powered load is always 0. Switch is open. There's no difference in potential here. Voltage across a powered load is always source if there's a single load. So again, we have a single load here. That load, or light bulb in this case, is going to be using all of the applied voltage. So voltage across a powered load is always source. Voltage across a load that's bad, or in other words an open load. Okay, let's say you have a light bulb and the filament is busted. That's what this is showing here. Voltage across a powered load is always source. Okay? Doesn't matter if the load is good or bad, because in this case, this is going to be treated like an open switch right in there, and you're still going to get 120 volts. Voltage across a full circuit is always source. Doesn't matter if the switch is open or closed, because you're measuring at the source location. To measure resistance of a circuit, you want to disconnect the circuit from the source. With resistance measurements, there cannot be any power on the source. Your meter actually is a power source. Decide what component or portion of the circuit you want to measure, disconnect the wires to, and remove that part. The part you want to measure has to be isolated. Set your meters to ohms. Touch one lead directly to another. This will show a reading of 0. That's to verify that your meter is working properly. If it doesn't, check your leads for damage and make sure they're plugged into the right spots on your meter. Now, touch the lead to one side of the component or isolated portion of the circuit. Wait for the number to stabilize and record that number. That's the resistance. Resistance is shown in ohms. So if we take resistance across an open switch, again, we isolated it. You see the openings right there. So we've isolated the circuit. Resistance across an open switch is always OL, or infinite, depending on your meter. Close the switch. Resistance across a closed switch will change to 0. Okay. So open switch is OL. And resistance across a closed switch, you'll see the meter right away change. Okay, OL will go away and it will change to 0. Resistance across a good load is some number. I can't tell you 0, 40, whatever. It's going to be some number. Resistance across a bad load or an open load is going to be infinite. Again, an open load or bad load or something with a broken wire internally is going to act like an open switch. To measure current, first step, you have to figure out which method you want to use. Okay, it's possible to use the clamp for higher voltage and currents. It's also possible to put a meter in line for lower voltages and current. Okay. To measure current with the clamp-on portion of your meter, and I'll show you an example in a minute. Okay, make sure the system is running. Clamp the meter around a single wire and wait for the numbers to stabilize. That's your amperage reading. Okay, if the current is too low to measure properly, consider putting the meter in line. And if that's not possible, wrap the wire around the clamp 5 to 10 times. Take your reading. Divide the number you get by the number of times the wire is ramped around the clamp. For example, if a wire is wrapped 10 times around the clamp and your reading is 2 amps, then 2 divided by 10 is 0.2 amps. So again, you can wrap that wire around the meter clamp if you have enough wire, or put a small piece in to replace. To measure in line, you basically open the circuit, put 1 meter lead on each side, so your meter is actually in series with the circuit. Your meter becomes part of the circuit. Be very careful on this because it's designed to be very low amperages. Okay, make sure the power circuit is turned off. Check your voltmeter to verify that this is the case. Disconnect a wire directly before the component you're concerned about. Put the meter in series with or in line with the component to complete the circuit. Make sure the meter is set to amps and the leads are plugged into the correct spots. Turn the circuit back on and allow the display to stabilize on the meter. Take your amperage reading. Make sure you know the levels of voltage and current your meter is rated for. This is why I said ask the directions. Don't exceed it. If you suspect it's close, use the clamp-on method. Meters cannot handle a lot of amperage going directly through them. Now, most of the time you don't have just one switch controlling something. Most circuits in HVAC industry, you'll have more than one control device. You'll have pressure switches, you'll have thermostats, you'll have other control devices. You have to be able to reliably and organized method to find the problems in the circuit. That's why most good technicians start off any diagnostic by using the hopscotch method to trace circuits. The procedure is very simple. First, make sure your meter is set on volts and make sure the leads are correctly plugged into the appropriate places on the meter. Next, check the voltage across the two endpoints of the circuit. In other words, line and neutral or line and line. That's your source to the circuit. You have to make sure you have voltage. Then, put one lead on the start point of the circuit. In the example I'm going to show you, that's L1. Keep that lead there. Use the second lead to go from point to point in the circuit before and after each switching device and loads to check for any place that has an incorrect voltage or opens until you find the problem. Okay, here's an example. Okay, we start off by line and neutral. We know we have 120, fine, it's a good circuit. You have power to the circuit. Then we go from line to the load line side of switch 1. Okay, 0 volts. That's valid because it's a complete circuit. You're not going to have a difference in potential. Okay, so we know this wire from line to switch 1 is good. Okay, we go from the line to the load side of switch 1. That means 120 volts. Okay, because switch 1 is open, so voltage across an open switch is source. Okay, you can verify that this is a problem by starting from neutral. Again, neutral to line is going to be 120 volts. That's your source. Then we go from neutral to the line to the neutral side of B1, 0. That's fine. Okay, voltage from neutral to the line side of B1, 0. Voltage remains 0. Again, non-powered load. It's not working. Then we go from neutral to line, so to switch 1 is 120 volts, problem found, switch 1 is open. Again, you have to remember, voltage across an open switch is 120. Okay, now I'm going to switch over to our simulator, okay, and let's go ahead and take us some voltage readings. Okay, I'm going to go ahead and switch over here. We have two bulbs in series, again, next to each other. My voltage is 120 volt source. We're going to go ahead and verify that. Okay, so I'm going to choose VAC on my meter. Okay, I'm going to put one lead there, and I'm going to put one lead there. Okay, my meter shows 240 volts. Now, I'm going to come down here. Actually, I'm going to leave that one. I'm going to take that lead, and I'm put it on the line side of bulb 1. So my leads are here. It's a wire. It's a plain wire. So it should have 0 volts. If I come across and move that to this other side of B1, I'm going to have 120 volts. That's fine. We haven't talked about it yet, but if I have two loads in series, they're going to split the voltage. So then I can come over here. Again, 120 volts tells me that's good. I'm going to come over here to my second side of my bulb, neutral side of bulb 2, 240 volts. That's fine. Okay, so that's voltage. Now, if I go over to amperage, I'm going to clamp the meter around. We're going to go ahead and clamp the meter there. I have 0.25 amps. I'm going to clamp the meter there, 0.25 amps. Okay, if I take that bulb, remove that bulb, in other words, now I have an open switch. Okay, 0 volts or 0 amps. If you take a look here, again, if there's an open in the circuit, which there is right there because I pulled the bulb out, we now have 0 amps. And if I put that bulb back in, you'll see the amperage go back to normal. Okay, so again, voltage, some pretty important concepts we talked about in this video. Voltage across an open switch is 0. or is source. Voltage across a closed switch is 0. Voltage across a load that is working, in other words a light bulb that is powered, is going to be source or some portion of source if they're in series. Voltage across a non-working load, in other words if this light bulb burns out, okay, I'm going to have source voltage but the load won't be working. Okay. So hopefully you got something out of this video. The only way to really learn how to use a meter is to practice using a meter.